resources of a country are its physical assets. How well or how poorly these are used determines the economic well-being of the country. The stands of timber in the forests of a country are a valuable resource, and when wise operation and conservation practices are followed, will provide a continuous supply of logs that can be floated to the mill and cut into various kinds of lumber for the building of homes, factories, and other structures, as well as to provide material for the making of paper and textile fibers. Water that flows in rivers and streams and is stored in lakes is a potential source of water supply. The ravages of floods can be eliminated for the most part, and the water of rivers and streams controlled by a system of dams constructed at appropriate places. Barren wastelands such as this can be transformed by irrigation into useful and productive land for growing crops. Water can be stored in reservoirs and brought to the consumer in canals to ensure an unfailing supply of the large amounts of water needed for domestic and commercial uses, and can provide electric power to improve the social and economic well-being of an area. In order to assure a continuing supply of basic materials such as iron and copper, new methods must be continuously found to seek out the wealth of minerals that lie hidden underground. Coal can be mined for use in heating homes, in operating factories, and for the production of power. Oil can be withdrawn and refined for use in heating, or as fuel for automobiles, airplanes, and power plants. Land that has become badly eroded can be reclaimed for crop production by contour plowing or by other modern agricultural practices. And the rich soils that nature has provided with abundant forage can be used for livestock grazing, or can be cultivated for orchards or crop raising as is best suited to the particular soil. Not so long ago, natural resources could only be located and evaluated by very slow, costly, and laborious work on the ground, much in the same way that the geologist examines rock specimens, and in the way the soil scientist samples, examines, and tests the soils. And the forester measures the diameter of the trees at numerous points throughout the forest. But today it's a different story. The aeroplane, equipped with an aerial camera, can provide aerial photographs by the use of which much of the costly, time-consuming search for natural resources by ground methods is eliminated. The telling of that story is the purpose of this film. In the following 4 sequences, we shall see examples of how the forester, the geologist, the soil scientist, and the hydrologist interpret aerial photographs to expedite their surveys. In this first sequence, we see how aerial photographs can be used to assist in making accurate and economical inventories of forest resources, and also determine the location and quantities of the various kinds of timber available. This forester will mark on the photographs information needed to make a forest inventory and map. He is using the aerial photographs and studying them under a stereoscope. In order to see the trees in 3 dimensions, He moves the two photographs until the images fuse as one. Then he sees the scene in stereoscopic relief and can estimate the kind and number of trees. We can follow his interpretation in this photographic view of the area. The pattern that we see is made by the tops of trees and tells us that it is forest land. Here the forest with dark tones contains softwood trees such as pine. The light tones are hardwoods, including oak and maple. The timber characteristics are marked on the photographs by a system of standard symbols. For example, the symbol HS2 bar tells the kind of timber, the general size and its density in this area. This parallax wedge is used by a forester to make estimates of tree heights. Other detailed observations are made with the many aids available to him. Such as this scale for measuring tree crowns. And this scale for measuring the general density of the trees, determined from the amount of ground area covered by the tree crowns. And this photo interpretation key that assists the forester in identifying the many kinds of trees in the forest. A scaled grid pattern is used to determine the acres of forest land. Each dot represents a certain number of acres depending on the scale of the photograph. With the information thus obtained from the aerial photographs, the forester can calculate the approximate number and kinds of board feet of timber in different parts of the forest. After sample checking on the ground, a map is made showing location, stand size, type, and degree of stocking of the timber throughout the forest. The map accompanies the analysis and report of the forest area investigated. And now we will see how the exploration and discovery of minerals are expedited by the use of aerial photography. Rock types and geologic formations can be identified on aerial photographs, and their positions and areas delineated. Here a geologist is studying geologic formations that he sees in 3 dimensions on the aerial photographs. Such details provide the guiding information needed to determine the mineral potential of the area. After carefully studying the photographs, he delineates the various features of geologic significance. And using standard symbols, labels the formations to indicate limestone, shale, sandstone, pebbly conglomerate, and so on. In some areas where thickening of conglomerate material occurs, commercial deposits of uranium and vanadium have been found. Stream gravels are indicated here by the letters Q, A, L. The symbols with arrows show strike lines and the direction in which the rocks are tilted, and the figures tell the degree of tilt. It is important to mark these features because they delineate geologic structures in which oil may be found, such as this major rock fold or upheaval running from the top left to the bottom right. Aerial color photography may be used because it is often better than black and white to detect certain mineral deposits. To the geologist, the different colors of the rocks in this high-altitude photograph may reveal something of their mineral content, whereas this black and white photograph, taken at the same time, shows no such differences. Despite the heavy vegetation in this area, parallel striations can be seen here, indicating a geologic structure known as a dike, along which important deposits of certain minerals are likely to be found. A ground observer standing here at the most favorable vantage point and looking toward the dike in this direction would get this view. In heavily forested areas such as this, more intensive ground observations have to be made to obtain these geologic details. This general-purpose geologic map has been prepared from information obtained by photo interpretation and verified by ground investigations. By using different colors and symbols, the rock outcroppings and other geologic features are indicated. The map provides basic information that will assist in the analysis and evaluation of the mineral resources of the area. In this third sequence, we shall see how aerial photographs are used to expedite the classification and mapping of soils, and how it can be done accurately and more economically than by ground studies alone. In the hands of the soil surveyor, the aerial photograph is a valuable tool that greatly expedites the mapping of soils. For example, here he examines and outlines an area that has a shallow soil with a 20% slope and moderate erosion. Working on the ground, the soil scientist examines the soil and notes characteristic features that will assist his interpretation, and also those features that are not determinable by photo interpretation alone. This is how the photograph looks after the characteristic features have been outlined and marked. Colored lines and symbols show the soil types and terrain conditions that have been identified by the ground inspection. Different kinds of vegetation and drainage can often be interpreted from aerial photographs and serve as an indicator of the soil beneath. For example, here we observe two main soil types. One type is easily recognized by its dark-toned vegetation and heavily dissected drainage, here, here, and here, and the other by its light-toned grass cover and widely spaced trees with little erosion or drainage pattern, here, here, and here. A ground observer standing at this point and scanning the area beginning here would get this panoramic view. You can see the sharp contrast between the two soil and vegetation types, just as detected in the aerial photograph. Without the help of aerial photographs, it is a very slow, laborious, and costly task to map their irregular boundaries. A close look at one of the sharp vegetation boundaries, such as this one here, is revealing. The change is abrupt. In the center of this scene, a kind of bush that thrives in one soil is dying out here, perhaps because it is unable to survive in the other soil type. Here the soil scientists are examining the deeper layers of the soil and collecting samples for laboratory analysis that will supplement the information recorded on the photographs. This information is necessary to verify the soil classification and complete the soil survey. A soil map is made from the information obtained by studying the aerial photographs and from the necessary on-the-ground investigations. By the use of colors and symbols, the map depicts the soil classifications and characteristics of the area surveyed. In this final sequence, we shall see how surface and groundwater explorations can be facilitated by the use of aerial photographs. The hydrologist who interprets these photographs under the stereoscope should have practical field experience in areas similar to the one he is studying and a general knowledge of its geology, soils, and vegetation. This heavy growth of water-loving plants here indicates a higher water table than in the adjacent areas. This is caused by the hills to the left of this area forming an underground barrier to the flow of groundwater. These cottonwood trees, planted by man to the left of this underground barrier, require much water. They must be irrigated by water from wells to the right of the barrier. Since they will not grow in areas where the water contains more than 1,000 parts per million of dissolved solids, their presence here is an example of the many inferences that the hydrologist uses to interpret the chemical composition of water. The red dashed lines indicates the underground barrier. Bodies of surface water are outlined in blue. Areas covered by vegetation are outlined in green, and so on for other hydrologic conditions annotated on the photographs. This photograph has been marked to show such significant hydrologic features as the shales and minor sandstones here. Their presence indicates a poor source of groundwater. The water in this river may have a high alkali content, as the hydrologist can infer from the geologic formations through which it has flowed. And this massive sandstone area, that is an excellent water-bearing bed, is therefore a good site for drilling wells to irrigate the valley below. On this photograph, the hydrologist has indicated the best site for building a dam, not only because the canyon is very narrow here, but also because his photo interpretation indicates that the rock formations in these canyon walls at these points are such that no water will leak through them if a dam is built. Also, by photo interpretation, he has outlined accurately the land that would be flooded. A topographic map could be made to determine the volume of water that would be impounded. This hydrologic map shows the water resources in a large area as developed by photo interpretation and verified by ground surveys. Blue is used to outline areas under which are excellent water-producing limestones and dolomites. Purple for excellent water-producing sandstones. Pink for shales with interbedded limestones and sandstones that produce only small quantities of water. Brown for poor water-producing beds of alternating shales, sandstones, conglomerates, and so on. Such maps serve as the basis for the fullest utilization of the water resources of an area. This new technique for locating and evaluating natural resources is being taught in a number of universities and training centers throughout the world, such as in this training center for the evaluation of natural resources, operated by the Pan American Institute of Geography and History near Rio de Janeiro, Brazil. Here, students from all of the American republics learn modern scientific methods and techniques that aid the important work of discovering and evaluating natural resources by photo interpretation. They are also taught the use of such scientific instruments as the airborne magnetometer. This instrument measures intensity changes in the Earth's magnetic field, indicating significant geologic features. And the airborne scintillometer, that measures gamma rays emitted by radioactive elements such as radium, thorium, and uranium. Such materials are searched for with the scintillometer. And this gravitymeter that is employed in determining the shape of the Earth and the geologic structures within it. Accurate knowledge of gravity is also needed for many special purposes, such as the development of new systems for navigation and missile guidance. In this center, the nations of America are having key personnel trained, not only in the discovery and evaluation of natural resources, but also how to use and conserve them. With this knowledge, they will be able to assist in the development of sound and expanding national economies, and thereby achieve a higher standard of living for their people.